Right now we're at a stage where the fluid simulation looks like this right here. So we have the ability to draw a container and then we can fill fluid into that. I think it behaves quite nicely, although it's not perfect yet, because if you fill a lot of water in the container, then it just won't overfill for whatever reason. And I still can't really explain what's going on here, so we need to fix that in this episode. And the first thing, after a lot of thinking about how we implemented the simulation so far, is that we actually should probably separate out the rules that determine how the water flows. So wait, let me just pull up the guide that we used as a reference point. So it was that one. Right. So this is a guide on how to implement cellular automata that implement liquids. And there are a couple of rules that determine how the water falls down and separates out to the sides. And in our implementation here, we loop over every cell in the grid and then apply all the rules to that cell. However, probably we should instead apply the rules successively. So we loop over every cell and apply rule number 1. Then we loop over every cell again and we apply rule number 2 to every cell. This probably solves some dependency issues between the different rules and between the cells, because if we apply all the rules to one cell, maybe we introduce some error. It just does not really feel right. So I think we should separate out the simulation into phases. And I would say we could implement new subroutines here, but also actually it doesn't really matter. We can do it all in one method as well. So we're going to have the water flow down rule here, and then we can extract the... Ooh, that's a big piece of code there. Yeah, then we can extract out rule number 2, which is this. Let me make it a bit smaller. Yeah, that should be okay. So we are looping over all the cells using rule number 1. And then we are looping over all the cells using rule number 2. So let me just copy the looping code here, the for loops. And then we need to add 2 closing braces. Let's see if that compiles. Of course it doesn't. What's the error? Source cell type is undeclared in line 116. So let's go to line 116. And that is this line right here. And here we don't have a source cell type. How is that possible? Okay, we have to extract it first. Right, and then we can also delete some unused integers that we introduced in the last episode, but we didn't actually use. For example, rule 1 applied. We didn't use it, so let's clean that up. Okay. Let's see how the water behaves now. Not sure if there is any improvement visible yet, but for sure, conceptually separating out the phases might be a better choice. It looks quite similar so far. can it overflow? That's the big question for me. No, it still can't overflow. For whatever reason. I think one problem is that there must be a problem in rule number 1. But let's see. I was actually yesterday when I went to sleep, I was actually thinking about how we modeled the problem a lot. And one thing that came to my mind is that it may be possible that we draw the water fill levels wrongly. So let's have a look at the water fill levels. So here, this is the water fill level, and the water height is the fill level multiplied by the cell size, right? And if the fill level is bigger than 1, then the fill level is not going to be kept. So it is possible that one cell overfills into the next one, and the next one then draws on top of that. So the fill level is not kept. So here we should do let's do that. Is the fill level multiplied by the cell size bigger than 1? If yes, then it must be 1, else it must be cell.fill level multiplied by cell size. So this is pretty much capping the fill level at 1. Let's see if that changes the simulation somehow. Oh yes, it does, but I'm not sure if that's correct. Surely it's not correct. So water height, cell.fill level multiplied by... no, of course not. We just kept the size at 1 pixel, I mean. So we have to check, is the fill level bigger than 1? If yes, then the water height is the cell size. Oops. If the fill level is bigger than 1, which is 100%, that means we fill the entire cell. So we set the cell size as the fill height, as the water height. Else we pick the cell.fill level multiplied by the cell size. Okay, I think this should be good. Let's see how the simulation looks like now. Let's draw a bit different shape today, or now. This feels okay-ish, but somehow the fluid levels sometimes drop down. I don't know why. I think I know why. This is because our rule 1 is still not sophisticated enough yet. So come on. Fill up. It seems to be overflowing now. Which is interesting. Before it didn't overflow. Which is a good sign. And then, right, there's a problem in our simulation rule number 1 that water only drops down if the cell below has a fill level that is bigger or smaller? Smaller, I think, than the current cell level. So the destination cell must have less water, and that's why the water stacks up in towers occasionally. And if you drop water on top of the tower, then it will drop down. It's a weird behavior. We have to refine that. Okay, but so far this is good. I like what we're seeing right now. And now let's have a look at rule number 1. So rule number 1 is water flows down. Maybe we should extract this into a new method. Let's do that, just to have some more clarity. So, and rule number 1 is simulation rule or simulation phase rule 1. And we apply it to the struct cell environment array of size rows by columns. So let's copy this. And we pass the entire environment. And also we should pass the coordinates of the current cell we're dealing with. Or we should pass the entire loop into there. Yeah, let's just copy the entire loop there. Okay, and now we have to, of course, call this simulation phase rule number 1 in here on the environment array. And since this rule number 1 is acting on the environment, it must also act on it must write the results into the next environment, so we need to pass another environment in here. J plus columns multiplied by I. Of the same size, rows by columns. And then we call phase 1 or rule 1 on the environment next as well. Then this is the execution of phase 1. No, maybe we can already encapsulate this next environment behavior thing in there. No, let's paste the next environment into here so that that the copying of the next environment is encapsulated within that method, and we don't need to pass it from outside. And then at the end of this method, we also write the next environment into the current environment. Let's see. Okay, so this is a fully encapsulated simulation phase that acts on the environment array. We don't need to pass any temporary array into it, and the results should be written back into environment at the end of that method. Now we can delete that parameter, and that should be simulation phase rule 1. And now let's create another method that is rule number 2, void simulation phase rule 2, and it takes as input. Can I just copy this? right here, and then delete that and paste. Yes. And here we copy that entire block of logic. Oh, I forgot a brace. And of course, we here also need to create a new environment next. This could technically also be encapsulated in its own method, but yeah, let's do it. So we create a method that returns a struct cell envir. I'm not sure if we can return empty arrays. I'm not sure about that. No, let's just leave it like that, just to have some more explicit code. If it's required, we can adapt it at the end of the method. And this for loop needs to be at the end of this method. And that should be simulation phase rule number 2. So let's compile the code and see if it still works. It should act just as if it was unchanged. And it's looking fine. Is it looking fine? I'm not sure. Yes, we do have some overflows, so that is good. Awesome. So yeah, the simulation is looking much better than before, because now the fluid is actually overflowing to the left and to the right, because we separated out the phases and thus eliminated the dependencies between the different phases. So we first drop down all the fluids, and only in the next step, in a separate simulation phase, we have the fluids spread out. So that is a good improvement. Let's see, we can even empty the fluids from that tank. So that's cool already. Next step, what's the next step? We have, of course, another simulation phase to implement, which would be rule number 3. We can do that, but it's not a priority now. I would like to focus on getting simulation rule number 1 done properly, because in rule number 1, which is this rule right here, rule number 1 determines that water flows down. However, it's I don't really like the rule on how much water currently flows down. So let's have a look at the document here. First, a cell will check to see if it is capable of flowing downwards into its bottom neighbor. Okay. And the amount of liquid that is allowed to flow into another cell is calculated based on the amount of liquid already in the source and destination cells. And this sentence right here is the critical one, which in my opinion, or in my understanding, messes up the simulation. Liquid will only flow if the destination cell has less liquid than the source cell. And that causes the hovering. But one thing that we definitely have to improve on is that we have to calculate the amount of liquid that is allowed to flow into the destination cell. So destination cell is this one. We check the fill level. It's smaller than the source fill level, so we can fill it, but how much liquid is allowed to flow down? Basically, we have to check how much free space there is in the destination cell. So let's check that. Destination cell. Maybe double free space destination, and that is equal to 1 minus destination cell dot fill level. That is technically how much we could fill into it. And if the free space in the destination cell is bigger than, or maybe bigger or equal than the source cell dot fill level, then we can just empty the entire source cell into the destination cell. Let's do that. So that is pretty much what we're doing here. So we have a source cell, the fill level is going to be 0, and the destination cell fill level is going to increment by the source cell fill level. Yeah, right. And then we have to also handle the case where the free space in the destination cell is smaller than the source cell's fill level, because in that case we can't transfer all the liquid. Free space destination is smaller than. Maybe it's just a simple else case is sufficient in that case. And here we can probably copy the fill level code here. And then the source cell fill level is not going to be 0, but it's going to decrement by the free space in the destination cell. And the environment next, the destination cell fill level is going to be set to 1. That should be it, I think. Let's see how that behaves in a compiled version of the program. So somehow the liquid is behaving more smoothly, but it's not really distributing well, and that is because of the rule that we have implemented, but which I meant is, of which I was not sure whether it makes sense. I mean this rule. Wait, where is it? Liquid will only flow if the destination cell has less liquid than the source cell. That is a rule. I'm not sure if it makes sense. That simulation looks okay now. I don't like these towers. I think the liquid should be able to fall down. Why not? Okay, anyways, but technically the simulation is already much better, in a much better state than before we started this video. So let's just do another quick test. We still have a side flow problem. Why is the liquid not flowing to the sides? Okay, so simulation rule number 2. Simulation rule number 2 is flowing into left and right neighboring cells. Once the cell has finished executing the first rule, it will then attempt to distribute its remaining liquid toward the left or right neighboring cells. The amount of liquid that is allowed to flow is dependent on the current amount of liquid in each cell. In the following images, you see that the liquid moves down. During the first iteration, during the second iteration, it can no longer flow downwards. Therefore, it flows into the adjacent cell that is available to its right. So we have executed simulation phase number 1, which is just liquid dropping down. And here we are dealing with simulation phase number 2, which is liquid flowing to the sides, but actually it is partially working because, well, have a look. Liquid is flowing to the sides, but if I add a border here and here, then it is somehow stacking up. So let me focus on the rules, even if it takes some time, but these are things that require some thinking. So I'm checking if the cell below is either full or solid or the bottom border, because only in this case there should be a flow to the side. So the source cell is this one, that is correct. If the next row is equal to the rows count, then we're dealing with the last row, so we have to separate out the fluid, that is correct. Then if the cell below, if the fill level of the cell below is bigger than or equal to 1, then we flow to the sides. Bigger than or equal to 1. No, rule number 1 was we can't flow down if the fill level of the cell below is bigger than the source cell's fill level. So we shouldn't, here we have to check that the environment, that the next cell fill level is bigger than or equal to, no, bigger than the current cell fill level. Columns multiplied by I dot fill level. I'm not sure about bigger than or equal to. Let's do bigger than, because that would be equivalent to this rule right here. Okay, and then we also check that and check whether the environment, whether the cell below is of type solid. So if, yeah, okay, that is correct. Let's see how the simulation behaves. That's looking good. Yeah, that looks good. I think that this is the way the simulation is intended to behave. Yes, I think it's working. That's awesome. Now we just have to adapt the graphics in order to get these partially filled cells illustrated properly. So let's have a look at the next rule. Because, no, we also have flowing upwards with pressure. After the cell has executed both rule number 1 and 2, it will then verify if it still contains more liquid than the maximum amount allowed. Actually, in our case, it's not possible to build up pressure because we properly check how much liquid can flow into the neighboring cells, I think. No, we don't check that in rule number 2. Yeah, so maybe it makes sense to build to create the pressure case as well. A pressurized cell will be allowed to flow upwards if possible. Yeah, okay. Let's just quickly, let's see how long that takes. Implement a new simulation phase. That is the case for pressurized cells. So that's going to be phase number 3. We first copy the environment, or we initialize the environment next array, and then we loop over all the cells. We check the source cell. We can delete pretty much all the rules starting from here. And in the end, we copy the result into the environment. So that is okay. Now, simulation phase rule number 3 is pressurized. How's pressurized pronounced? Pressure. Correct. Okay. Cells can release fluid upwards. Okay, let me fix the comments here as well. And let's do the same for rule number 1. Oh. Okay, so we are dealing with rule number 3 now, so let's put that in writing here. And in rule number 3, we need to check. Check if source cell's fill level is bigger than 1. And also we need to check if there is a water cell above into which fluid can be transferred. So we have the source cell. Then if the source cell dot fill level is bigger than 1 and there's a cell above, we can only check the cell above if I is bigger than 0. And let's get the cell above. Environment at j plus columns I minus 1 dot fill No, dot type, it must be a water type. Type is equal to water type. Then do stuff. So if the source cell's fill level is bigger than 1, that means there is pressure. Then we can only release pressure in case there is space above. So we can't be in the topmost row. And then we have to check that the cell above is of type water. So because we can't release fluid into a solid cell. Oops. Okay. No. Why did the simulation just look so weird? It looked like we did not make an improvement at all. We need overflow. No, here it looks okay. Interesting. But it was just stacking up. Huh, weird. Okay. So if the cell is pressurized and water can flow up, then do we release all of the fluid at once into the upward neighbor? A pressurized cell will be allowed to flow upwards if possible. After the cell has executed both rule number 1 and rule number 2, it will then verify if it still contains more liquid than the maximum amount allowed. If it does contain more liquid, then the cell becomes pressurized. A pressurized cell will be allowed to flow upwards if possible. So how much water is, or how much liquid is released upwards? We could technically do and release everything at once. Or we could create a rate of release, but that would be, for that we would have to make an educated guess or somehow have knowledge about the viscosity we aim to achieve or whatever. So let's just try to release everything possible. So we do double transfer fill, that is the source. Maybe the cell above should also have less liquid than the cell below. That is something we should check for, I think. And source cell dot fill level must be bigger than the destination cell fill level. Environment J plus columns multiplied by I minus 1 dot fill level. Because if the cell above has more liquid than the cell below, even if both have liquid levels bigger than 1, then first the cell above should release its fluid and not the cell below. So, yeah. Okay. Source cell dot fill level minus, let me create a destination cell here, I'm not sure if we even need it that much, because this is just a copy of the cell. And we actually want to act on the real data. So that's why I use the array index all the time. Columns multiplied by I minus 1. If the source... okay. Destination cell dot fill level. That is the amount of liquid we want to transfer, and we will transfer all of it. Let's just get the current cell, columns multiplied by I, and in the source cell we decrement the fill level by... no, we have to make sure that the source cell fill level we only want to transfer up what is bigger than 1, so we have to do source cell fill level minus 1. Let's try it like that. That is going to be what we're going to transfer. And we decrement the source cell fill level by the transfer fill, and the destination cell fill level, we increment that by the transfer fill. And it's not I plus 1, it's I minus 1. Otherwise we would release pressure downwards, which is possible, but it should be handled by rule number 1. So let's compile and execute. Let's see how the fluid behaves. Let me just make a bit more complex structure, just for fun. I think it works. The only thing that is still apparent to me is that when I try to draw into a cell that is already full, it does not overpressurize, because we draw cells and just set the fill state to 1. We could actually build up the pressure if I click with the mouse into a cell that is already filled. Let's see. Can we do that? So we create a fill level here. So that is the mouse handling right here. If we click into a cell, we create a new cell with a fill level right here. If we delete a cell, it's going to be 0. If we fill a cell, this fill level is going to be 1. So here we fill a water cell. Let me just do... this, we have a cell, and then we... Oops. In case we delete, we set the cell to be the water type with a fill level of 0. So let's just say fill level is 0. Then we can probably delete this line of code. No, we have to replace that with a semicolon. Okay. Now in case we delete, we set a fill level of 0 and then we create that cell. In any other case, I would like to build up pressure. Else, we still set a water type cell. That is fine. And the fill level should be 1. No, the fill level should be... No. Wait. The fill level, the new fill level of that cell should be the original cell's fill level. So let's get the original cell's fill level. Environment, add cell X plus columns multiplied by cell Y dot fill level. Oh no, we can just increment the fill level here without creating a new cell. Wait. No, let's just do it like that. So this should work. I hope it works. Yeah, and I messed something up. We can't draw solids anymore because something here is wrong. So we have the cell, we have the current type. But where's the solid type? Current type is solid type right here. And we switch the type in case we press the space bar. Okay, probably it needs to be done like that. And the fill level is incremented by 1. That doesn't matter for solids actually, because they are always handled as solids, but so we can leave that piece of logic there. Yeah, let's try. That looks good. And let's see what happens if I draw inside the piece of liquid here. Nothing. But actually, I would expect that we build up pressure in these cells if I draw here, and that the liquid overflows then. So the fill level is the current fill level plus 1. Maybe we didn't simulate phase 3. Yeah, we forgot that. Oops. Okay, let's see. Now it should be working. So here's our container. Here's our other container. And let's see what happens if we let some liquid flow into there. It's already working nicely. Hyper-realistic fluid simulation. No, I'm happy with it. And now if I draw... No, damn it. Let's see. Can I build up pressure if I draw in here? We can't really see it because it's too much going on. No, the pressure doesn't really seem to build up if I click the mouse button in existing liquid cells. So what's going on with the pressure? There's our simulation phase number 3. If the cell is pressurized and water can flow up, the cell is pressurized and water can flow up, the transfer fill is the source cell dot fill level minus 1. Then we decrement the source cell's fill level by the transfer fill. Which is practically the same in this case as setting it to 1, because we let everything else flow up. And then increment, and also because we make sure that... no, it's not the same. No, forget about it. And then here we let the environment, the cell above dot fill level be incremented by the transfer fill. Let me just put a printf in here. Printf transfer fill. Just to see that actual values are in the range where I would expect them. Okay, something's wrong there. Ooh. Yeah, I know why. Yeah, because we have to write into the environment next. Because we're simulating based on the current environment, we're writing the values into the next environment, and then we're copying the next environment into the current environment. So let's see what happens now. Now we have a bug that makes... well, we have to check whether a cell is a water cell, because solid cells can't overflow. So if the source cell dot type is equal to water cell, because right now we have the case where the solid cells just overflow, which makes no sense. Also, we increment the pressure on the solid cells, which makes no sense, but it shouldn't be a problem. As long as they are properly handled, we can just ignore the pressure value there. Let's see, now I would expect it to be working. Yeah, it does work. Because if I press here now, the pressure is building up, as you can see. And it's reducing down. Yeah, the problem is that maybe pressure is building up too quickly with the mouse button. So that's why we get this water fountain effect. So let's fix that. So if I press with the mouse button into a cell that is already filled, or actually into any cell, let's just increase the pressure, the fill level by 0.2. Okay, now we get no drawing of water. Why? Now we get it. Yeah, the behavior is logically correct, but it's not. It's physically a bit unrealistic. So I would like to adapt this a bit. Why doesn't it draw the fill level? if maybe let's fix it like that. We don't delete a cell. If a cell so if the current cell's fill level is already bigger than 1, then don't increment it too much. Then let's just say the fill level should be the current environment cells fill level plus, let's say plus 0.2. Else else the fill level is going to be one. Let's see. I expect this to be working. There's a syntax bug somewhere. Why? J is undeclared. Ah, yeah, because I use different indices here. So columns.y, columns underscore y, columns, not columns, cell y plus columns multiplied by cell x. Oh, and I forgot compiling. So let's see. Yeah, this is good. This is okay. Let's see how we can build up pressure. No, it doesn't really add up any pressure. Still, I like this more than adding up pressure. But why? But why is it not working? If the environment cell's fill level is bigger than 1, well, it is never bigger than 1. Maybe let's do bigger than or equal to 1. Maybe that's what we're missing. Oh, now the fluid state is actually decreasing. Why? Fill level is equal to the current fill level. Did I mix up the x and y here? Not sure. if the current cell's fill level is bigger than or equal to 1, then increment it by, what happens if we do 1 here? Somehow this is partially working, but it's somehow odd. Now let's forget about this weird case where we increase pressure within the fluid. I think somehow it's behaving oddly. I would like to focus on the simulation itself. So we have to do, let's delete all of that. And let's do a fill level is equal to 1. Let's see how that behaves. Yeah, that's much better. Okay, now I would like to introduce some graphics, and there's a new rule for that. Rendering falling liquids, and this is exactly the case we're having right now. When liquids are falling, we have these lines that are falling down, and that looks quite odd, not really beautiful. Liquids that are falling downward do not render very nicely, as they sometimes only contain a small amount of liquid in the cells. Rendering the amount of liquid directly in these cells can look somewhat strange. Yeah. If we add a check to see if the liquid flowing downwards, is flowing downwards, we can render these cells as having a full unit of liquid. This is mainly to make the simulation render a little nicer. Yeah, okay, so how do we figure out that the liquid is flowing downwards? This should be a rendering problem, so it is not part of the simulation itself, but rather a problem of drawing the cells. So there should be this should be doable in the draw cell function. And how do we determine if the cell is flowing downwards? We could technically add a flag here, int flowing down. Is that a good idea? I'm not sure. How do we determine if a single cell is flowing downwards? Technically, we would have to check all the neighbors and reevaluate the logic of rule number 1 again. Maybe it makes sense to maybe we should have a... I'm thinking of many solutions now. Either we can introduce a new flag flowing down here. That would mess up pretty much all the definition of the cells that we have in the entire piece of program. Or we could introduce a new 2D array. A new array that for each cell determines whether it's flowing downwards. So that would be a separate data structure just for rendering, because I'm not sure if this should be part of the cell data model. And probably it's the most straightforward solution. So let's introduce flowing down. A flag set by the simulation routine indicating whether the fluid is flowing down at this time, at this simulation step. Okay, and if the fluid is flowing down right here, so where was this? We have the destination cell. Oh my God. No, let's make it more simple. I have a new idea. It should be a pure rendering problem. So here we determine the water fill level. And we can check, is the cell below the current cell? We don't know about the cell below. Oh no. So the question is practically, is the cell below the current cell completely filled? If not, fill it. There's no indication in this guide on how to implement that. We had to check to see if the liquid is flowing downwards. We can render the blah, 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 blah. Oh, then let's go ahead with this, with the flag flowing down. How do we determine if the cell, if the water is flowing down? We have to set the flowing down in the destination cell also, I think. No, this is way too, this is not good. I would say the following. We draw the environment and we draw the individual cells here. However, we can do a second loop for going over all the columns in the simulation and checking if successive water cells are continuously filled. Maybe that's an idea. 0. So we draw the individual cells there, and then we fill water cascades. Is it called cascades in English? I don't know. Cascades and fountains to be continuous. So I would like to loop over over the for every, I would like to loop over the rows. Okay, so going down the rows, and of course also looping over columns. But I would like to go to move column by column probably. So maybe we have to switch those two. So going down column by column, we do the following. Check if the current cell is between two water type cells with a fill bigger than 0. So let's try to do this check. We have to first check, is the row bigger than 0? And the row must be smaller than rows. I think minus... not sure about that. So we check the row boundaries. If that is the case, check cell above. So let's check the cell above. Environment. Add j plus columns multiplied by I dot fill level bigger than 0, and the current cell's fill level must be bigger than 0 as well. So environment j plus columns multiplied by I dot fill level bigger than 0. Right. We have to also check above here, current and below. And the cell below must be filled as well. Or no, does the cell below even matter? Maybe not, maybe not, maybe not. Maybe the cell below doesn't matter. Let's try this. If that is the case, then fill cell and we pass the current cell. Fill water cell. Maybe we can use draw cell, but with an extra parameter. We draw the cell to the surface, we pass on environment at j plus columns multiplied by I, and then we say draw cell and we pass a 1 that indicates whether to completely fill the cell. So this is another rendering step. Int fill cell. So if the water type cell is, if fill cell is 1 or is not 0, then we completely fill the cell. Or let's do this. If the fill cell value is 0, we don't fill the cell completely, and we calculate and you follow this old logic here, but if fill cell is 1 or any other value that is not 0, then we call fill rectangle on the cell rectangle, which is the entire cell. Cell rect. Okay, now I'm really interested in how that looks. How does that look? No. No. That does not work. So the cell above must have a fill level that is bigger than 0. And the current cell must have a fill value that is bigger than 0. So what exactly is wrong here? I'm not sure. What happens if we disable this cell drawing? Does the simulation still work? Just to exclude that we messed anything up. Yeah, that looks good. This looks very good. That's trash. But it looks like, since we have a seemingly arbitrary border here, that rows and columns are somehow swapped. So here we're telling the draw cell function to draw the cell at j plus columns multiplied by I. That should be correct, shouldn't it? What if we change this again? This actually shouldn't make a difference. Okay, something isn't working. of course, yeah, I messed up. Now I need to create a new pane here, get my processes and find it and kill it. Where is it? That's the fluid. 1685. That should be it. Now it should be working. Let's see. Yeah, the behavior is still the same, so something is still wrong. So we loop over all the rows and columns and check if the current cell is between two water type cells. Do we check if the current cell is between two water type cells even? No, we don't check that. If I is bigger than 0 and environ, let's just introduce a struct cell above, and that is the cell above environment j plus columns multiplied by I. Check if the current cell is below a water type cell, not between two. We just need the cell above, I think. So we check that cell above dot type is equal to water type. Then we check, and of course we also check that the cell above dot fill level is bigger than 0. And I messed up here. I need to reference I minus 1. That is the cell above. And here we can replace that call with, oops. With the cell, let's call it cell current. Cell current. So the cell above type must be water type, and of course the current cell type, cell current, must be water type as well. Probably this check is superfluous, because we also check that in the draw cell method, but it doesn't harm to check it here as well. Cell current dot type is water type. Then we check the cell above dot fill level is bigger than 0 and cell current fill level is bigger than 0. And then we draw the cell. Let me just confirm that the logic is still okay by commenting out that the graphics part. Yeah, that looks good. And drawing the cell here, we draw to the surface, we draw the following cell. So there must be an interesting and probably incredibly stupid bug somewhere around here that I haven't found yet. So, yeah. We use the cell rectangle here. What is that? That should be correct because the solids use that same cell rectangle. If the cell type is a water type cell, if fill site cell is false, then we calculate the heights of the rectangles to be drawn. Else we just create a completely filled block. This is interesting, but these are the kinds of errors where I'm 100% sure that they are completely stupid and I just don't see it. And probably you already see it and you are wondering for the last 20 minutes what the hell I'm doing, but I haven't found it yet. So this is the one, I. This is also J, all J's. The cell above is the environment at J plus columns multiplied by I minus 1. That's the... Is it? What if I just turn that around here? For some reason, I have the impression that this is an error that has to do something with these indices. No, okay, good. Okay, that's good. It's not an error related to that. Yeah, but what the hell is that? I have the impression that our rendering here even somehow changes the simulation because the simulation looks completely odd. How about we... let's just change this to 1. So in any case, completely fill the cell. Yeah, of course, this is stupid. So if I is bigger than... Oh, let's have another look at that. Wait, I think it was interesting. So the first row is not being colored because right here we have this I bigger than 0 check. All the other cells are colored because they are water types. Of course, they don't have a fill. So that's messing it up. And here, that's why we check the fill level. It must be bigger than 0 for the cell above and the current cell. We check the cell above, we check the current cell. We check the cell above's type, and we check the current cell's type. Cell above dot fill level must be bigger than 1, and the cell current dot fill level must be bigger than 1 as well. Bigger than 1? No, I mean bigger than 0, of course. What the hell is that? Could it be that our model is so precise that it will distribute fluids out to the sides in tiny, tiny fractions that are of size smaller than 1 pixel, so that we don't see them, but with this new code we actually see them? This might be the explanation. Because we spread fluids to the side, but in very tiny, tiny amounts probably. Let's check if the fill level is not bigger than 0, but bigger than 0. Whatever, 0.01, for example. Aha. So this is already behaving very differently. Although it's still not the same. But I think this is the explanation probably. And checking 0.1s here, or the fluid state here, is probably not entirely correct. We maybe have to... Oh, okay. No. 0.1 is too much. Let's try 0.02. That's good. Not perfect, but it is okay. Maybe this pattern, checking the cell above and the cell below, is not really good. It shouldn't depend on the cell above, actually. Let's see what happens if we check the cell below. If the cell below So let's string replace that and replace it with a comment. Oops, something is wrong. So let's comment it out. The cell below is the cell at +1. Here we have to check also that I is bigger than rows -1. Let's see what happens now. So the cell above, in this case, let me just rename it. Cell above, rename it with cell below. The cell below and the cell current. If the cell below is a water type and the cell below fill level is... Doesn't really matter actually what the fill level of the cell below is. But the cell current.fill level is anything, then probably it will fall. No, we have to check, is the cell current.fill level bigger than the cell below dot fill level? Let's see. If the current cell's fill level is bigger than the fill level of the cell below, then maybe we should draw the cell below as one block of water. I don't get why it doesn't work. I mean, the water simulation is working, but the graphics are not the way I intended them to be. Yeah, of course. I'm so sorry if you have to endure this. Of course, I needs to be smaller than rows -1. Let's try this again. This doesn't work, obviously. Let's draw the current cell at I. What the hell? If the current cell.fill level is bigger than the cell below.fill level and the current cell.fill level is of any significance, let's say it's bigger than 0.2, what's wrong? Cell current.fill level. So the cell below has to be a water type, the current cell dot fill level has to be bigger than the cell below dot fill level. Yeah, then Maybe we should try this again. I don't really like this rendering stuff after it has been completely calculated, actually. How about... Yeah, this would be violating the guide. But how about we forget all of this weird rendering here? So let's just... Should I delete it? No, I will comment it out. So let's keep it commented out and let's just in draw cell forget about this weird fill cell thing. We don't need any fill cell. And here in draw cell we can also remove that. Let's try to find a way to interpolate the colors a bit. So we fill the water. If a cell is a water type, then it should be wait, let me figure out. I'm just thinking, if there is if there is less water in a cell, why not let's just try drawing it a bit darker, for example. Then to do that, we would have to figure out how to interpolate colors, because I would like to be the blue, the maximum value, and this and black probably the minimum value. So we would have to we have to get somehow a color that is a UN32 interpolated color, and that is between, and we interpolate between get interpolated color between color black, color blue, and then we pass on the cell dot fill level, which is or should be a value between 0 and 1. Cell dot fill level. Okay. And up here we create a method that returns a double. Get interpolated color. We provide a UN32 min, UN32 max, and we get the cell dot fill level. Sorry. Double percentage. And the blue color that we're using is this one right here. So how do we really interpolate this in black? We would have to... Oh no. This is a color specified by 3 numbers. Oh, we would have to figure out what all these bits indicate in STL. STL color. Oh, wait. STL color UN32. RGBA. What is A? A is alpha, I think, which should be the opacity. RGBA color. Let's have a look. Red, green, blue is RGB. And then there's RGBA, which is alpha. And alpha is the opacity, right? And this is what we would need for the interpolation, I would say. So we actually only need to change this last value. So let's see what happens if we change the color blue. Color blue. And append FF here. So this should be the alpha value. Looks whitish. Maybe we need to append it here. Yeah, probably. Okay. So this is now our color blue. And if we change the alpha value, we should get a bit more opaque colors. No, that's not really opaque. That's not opaque either. I really don't like that color, that the water is just hovering above other pieces of water. And what we're actually trying to solve right now, what we're actually doing is, through graphics, by interpolation and all this stuff, we're trying to get rid of those lines. Maybe we should just implement rule number 1 properly and violate the guide that we found online. Let me delete all of that here. We don't need it. So let's go back to rule number 1. There's a free space in the destination. 1 minus destination cell.fill level. But we only transfer liquid if the destination cell level is smaller than the source cell fill level. But that is stupid. How about we just check if the destination fill level, the destination cell fill level is smaller than 1. Okay, for some reason that doesn't work. Let's forget about this piece of code right here. Okay. Maybe we can do the interpolated colors later. And let's just check that the fill level in the destination cell is smaller than 1, and then that should be sufficient. No, this is not good. How much liquid can flow into the destination cell? Oh! That looked good for a brief moment, but now it's trash. No. Maybe just sticking to the rules is not as bad as I thought. Okay, let's try the interpolated colors approach again. So we interpolate colors right here. We should be able, if we just return, no, we return a uint32, not a double. We return color blue, then this should be equivalent to the code we had before. Yeah. Now, how does it look if we return? If we somehow let's just try to subtract min minus max, max minus min multiplied by percentage. This is a regular interpolation, but I don't know what it does to color values, because probably everything will get very colorful now. No. Ah, yeah, we don't use the interpolated color yet. Yeah. Awesome. Let's see, we interpolated the color. I'm not really happy right now, because we should be able to get it to a state like that, because we followed all the rules. Okay, let me introduce the fill cell value here again, and if we fill the cell, if fill cell, then we fill the cell rectangle. Else right, now we fill the cell, so we have to provide the entire the entire cell rectangle. Let's see how that looks like. Of course, we have to adapt the call down here. And let's just pass a 1. So this should give us filled cells all over the place, which is not something we want. That looks interesting, however. Actually, it looks quite... Why does it look good? Interesting. So this is not a proper interpolation, so let's just change it to return blue color no, color blue. Of course. Maybe the interpolation was better. But it's of course not done correctly. We have to somehow shift the bit values in the RGB colors somehow. Maybe we should calculate an alpha value that is pretty much the percent. Oh no, 255 multiplied by the percentage. And then that is written into the alpha value. And then we return the color. And that is practically its color blue. However, we would like to change the alpha value of color blue. So how do we do that? We need to somehow shift the color. I'm just looking up how to interpolate the alpha value of a color. It's not, shouldn't be hard. Or can we just do that? Wait. Let's forget about the alpha value part and let's forget about this part and let's just try return max minus min multiplied by percentage plus min. So that is what I forgot earlier. No. I think we have to interpolate the individual channels. Yeah. Okay. Now let's try to do that. Color is this is really complex. I'm not really a fan of these byte shifting things. So we need to get the max. Let me just copy this. So we have color, the red channel 1 is coming from, yeah, color 1 is, color 1 is max, color UN32, color 2 is min. Fraction is percentage. It won't work for sure. Yeah. Maybe we need to first of all switch max and min. Oh, it's working. It's working. Gosh, it's working. It's somehow like gas because we don't have a strict border. But it is a working fluid simulation. let's just capture the fluid here. Yeah, it's working. Should we quit at this point? I'm not sure. So we can draw containers. For example, like this. Let's see how it works out. I actually like it the way it is. I actually really like it that way. Let's just... What is something we can test right now? Maybe we should test a bit more fine-grained simulation, because right now we're dealing with a pretty rough grid with a cell size of 10. Let's change it to 5. Let's remove the line width, so no lines are going to be drawn. Let's see how that looks like. So we can draw containers. Like that. We can still delete lines. We can make fluids probably go here. Let's see. The fluid is not spreading quickly enough, in my opinion. So this is really behaving like gas. But the trickling down here is quite nice. It's definitely an interesting project. It's definitely interesting. Let me change the cell size to 10. Reintroduce a border of size 1. Not sure if you can see it in the video. Let me draw something here. I mean, it's working. Maybe it looks so gaseous, so much like a gas, because the minimum value of the interpolated colors is just black, and that's just too dark, so it looks opaque. But maybe we should get an interpolated color between two different blues. That would probably improve a lot. So let's get a hex. Wait, where is it? Color picker hex. Let's get a blue here. For example, let's get this strong blue with a hex value of that. And let's define color blue min, and that is going to be this value. So we do that, and then we have a color blue. Color blue max, which is this value. And let's have a look where where the color blue is used in the code. Yeah, so here we need to provide color blue min. Then here we need to provide color blue max. Then let's look for more occurrences of color blue. And that's it already, it seems. Let's, no. Yeah, I don't want, of course, a blue background. Let's say that a cell that has a fill state below a certain threshold should be black. Yeah. So a cell, if fill cell. Get interpolated color, cell fill level. We'll just hack this into the get interpolated color method. Oh no, let's do it here. If the cell.fill level is smaller than 0.05, for example. No, smaller than 0.1. Then interpolated color is going to be color black. Let's see how that looks like. This looks good. This is finally something where I'm saying, okay, this looks good. So let me just increase the cell size again, just so you can see it better. Yeah, this is nice. This is finally something that is nice. Where's the water here coming from? Ah, it's overflowing from the central container. This is good. Yeah, I really like that. Happy with that. Yeah, so this episode was really a long odyssey. We tried so many different approaches. The problem is not simulating the water itself, but properly displaying it in a way, or displaying the fill values in a way that the water does not look like a gas. It does not look like a gas, and instead it actually looks like water. And so you can't just interpolate surfaces, or you can't just interpolate water fill state colors, and also partially coloring cells comes with problems, which we saw, because then you have to figure out how to render the cells between the partially filled cells, which often look quite ugly. But this is really, I think this is a good solution. It works. It does not require any post-rendering as the other solution we tried before that. So this is really a water simulator where I can say, okay, that's a good stepping point for the water simulation project. We have some nice watercolors. It's just cool. So let me just create one more scenario, which we can use for a thumbnail. And as a final experiment, I will introduce a container here. Maybe let's pass a pipe. Let's create a pipe here that can, oops. So let's create a container here. Then let's create something like a pipe here that can capture all the water coming down from the container. And that pipe will lead the water into this container. Oops. into this container right here. So let's draw some water and see what happens. And we can probably delete this cell and let the water trickle down, and see how it looks like. So this is really cool. This is really cool. I'm really proud of that project because it was really, really complex. And considering that just 2 months ago, I had no idea about C as a programming language, I'm quite happy that we're now at a stage, or I'm now at a stage where actually something usable or something that is visually appealing comes out as a result. So that is really cool. I hope to see you next time as well. Please subscribe if you want to see more C programming videos. Also check out the older videos on this channel, because then you will really see the progression we're making together, and it's awesome. It's really fun. So see you next time. Bye.